All right. So I've started recording. Just make sure your mics are off, and then you can turn it on when you have to say something. Yeah?
Noted.
Okay. Right. So Newton's laws of motion. Right. So I will expect that you guys went through this. Um, there's nothing much I can explain here. You just need to go through these definitions of Newton's laws of motion. Right. You will see um, I have defined them from my own perspective, right? So using my own understanding, right? With Newton's laws of motion, it is important with any definition. In fact, it is important that you understand it in a way that you are able to define it using your own words. Nah? So just make sure you go through this, and then if you have questions, um, we will go. I can go through those questions with you, right? If you look how I did this when looking at Newton's first law of motion, right? I showed you the principle, right? How we define Newton's first law of motion, and then I made a relation to Newton's first law of motion with what with inertia, and the reason why we are able to say Newton's first law of motion can be referred to as the law of inertia, right? Did you make that connection?
Yes, sir.
Wonderful, right? Wonderful, wonderful. Hence, I'm saying, if you went through this with an understanding, then you should be fine because my explanation is going to be like how I have, what is this? How I've written these notes for you guys, right? Similarly, with Newton's second law of motion, right? I wrote down the definition of the law and then related it to how the formula F net is equal to ma, right, comes about, right? Or rather, let me say how we express Newton's second law of motion mathematically, right? It boils down to momentum and impulse, right? So if you went through this, right, you know exactly where this formula comes from. F net is equal to ma, right? And then if you look at even the definition itself, right, Newton's second law states that the rate of change of linear momentum is directly proportional to and in the same direction as the net force, right? If you look at this impulse momentum theorem, right, so it comes from momentum being equal to impulse, right? So that's the impulse, that's the change in linear momentum, right? Now, what is this impulse, right? Impulse, this is the formula for calculating impulse. It's F net times change in t, right? And the formula to calculate momentum is m times v, right? So that means to calculate the change in momentum, right? Because for solids, right, under dynamics, we'll essentially just be looking at solids. So between mass and velocity, right? Between mass and velocity, which of those two do you think has the potential to change? So that was a question.
Velocity.
Velocity, exactly. Right. So meaning to calculate the change in momentum, right? To calculate the change in momentum, since we've established that the only quantity that can change here, since we're only looking at solids, is velocity, it means the change in momentum will be mass times the change in velocity, right? That is where this here comes from, right? This, right? That is where this comes from, right? So change in momentum is equal to mass times change in velocity. Change in velocity we know is equal to final minus initial velocity, right? So change in v is equal to final minus initial velocity, right? This is how this is how final velocity is denoted, or this is how I denote the final velocity, and this is how I denote the initial velocity, right? And then from this, then, if you solve for f net, right, it means you're going to divide both sides by changing t, right? This is what you end up with. F net, as f net is essentially equal to the change in momentum divided by the change in linear momentum divided by change in t. Now, if you look at the definition, right, of Newton's second law of motion, it states that the rate of change of linear momentum, right, if you look at this formula, F net is equal to change in V over change in T. This essentially, theoretically, is the rate of change of what? Of momentum, right? Is directly proportional to and in the same direction as F net. So essentially, the rate of change of momentum is directly proportional to and in the same direction as F net. That is where this comes from. F net is equal to MA, right? If you are able to make this relation for dynamics, right, it becomes very easy, right? If you know where all the formulas, or if you are able to derive any and all the formulas, right, it becomes convenient when having to do exercises on dynamics, right? It just makes it very simple because any one of these formulas you are able to use as long as you know and understand where they come from. Are we clear here?
Yes, sir.
Yes,
Right.
sir.
So make sure you go through this here. Right. I didn't do this. Right. I didn't write these notes for fun. They're for you guys to go through. Are we clear?
Yes, sir.
Yeah.
Sir.
Right. And then there's Newton's third law of motion. That one I don't need to go through. That one is probably the easiest one. Mathematically, it is the same as saying the sum of forces going up is equal to the sum of forces going down, or the sum of forces going in that direction is equal to the sum of forces going in the opposite direction, right? Newton's third law of motion is essentially this here, mathematically, right?
Yes, sir.
Yes, sir.
Right. So this one we don't really need to go through, right? Now, there's another. So all of these formulas, or let me say, right? So as far as Newton's laws of motion, the most important one for dynamics is Newton's second law of motion, right? All of them are important, but the most important one, the one we'll be applying the most, is Newton's second law of motion, right? Because it's through Newton's second law of motion that we get this F net, right? And then also when looking at forces that an object is being subjected to, whether that object is on a horizontal plane or inclined plane, right? The way we consider direction is by essentially looking at the direction of the forces relative to the direction of acceleration, right? So for vectors, maybe let me not say vectors, but for forces in particular, right? There's two ways in which we can consider direction. One of which is by using the Cartesian plane, right? So up is positive, down is negative, right is positive, left is negative, right? So that's what I mean. The second way, which is the one we are going to be using, is through using the direction of acceleration, right? So we consider forces going in the same direction as acceleration as being positive, and forces going against acceleration as being negative. Are we clear?
Yes, sir.
Yes, sir. Yes, sir.
Right, so that is the one we'll be predominantly using, right? Where we look at the direction of the forces relative to the direction of acceleration, right? And then the forces going in the same direction as acceleration, those you take as being positive. Forces going against the direction of acceleration, those ones we take as being negative, right? Right, so this is a very important formula, right? So this one, well, this one and this one, right? It can work to your advantage. So make sure you understand and know both of these formulas, right? Also, with engineering science, guys, I would advise that you do as many problems as you can so that the formulas essentially stick in your mind, right? Because I can tell you right now, if you need to go, if you're in the exam setting, right? If you're in an exam setting and you need to go to the formula sheet, just know you're in trouble, right? So avoid having to go to the formula sheet, because if you need to go there, it means already you are under stress. Being under stress, if you go to the formula sheet, every formula is going to make sense. You will find yourselves using formulas we've never even used before, ever. Do you see what I'm saying? Hello?
Yes, sir.
Yes. Yes, sir.
Right.
But what is the best way of reading the formula sheet? Just
So
to
this is
remind you,
a quick
there are a lot of
question.
Okay, wait. Say again. The first guy who was saying something. I didn't get that. You were saying something about the formula sheet. I'm listening, Chief. Okay, this
Hello,
guy.
sir.
All right. Continue, my guy.
Yes, sir, man. I just spoke to one of the guys that I normally practice with, and he says he's still at work. He's got a breakdown at work. So I just want to confirm if you are recording just for people like him.
Oh, of course. Oh, of course, my guy. I'll be posting this lesson in my channel, and then I'll send the link in the group. So don't tell him not to worry.
Okay, thank you, sir.
Right. Is that other guy back? Still not back. Right. Okay. Let's continue then. Right. Now, another formula that is convenient to know for dynamics, right, is a theorem I call the work energy theorem, right? Work energy theorem, right? This formula is going to come in handy as well, right? Work energy theorem, right? Let me see here, because I don't remember. Okay, I didn't. Right. So work energy theorem, right? Work energy theorem is part of the formulas we use for energy, right? So we're going to look at other formulas that we use for energy as well, right? As far as the definitions, yeah, that you can go through on your own, right? So by definitions, I mean what potential energy is, kinetic energy, all that, right? That part you are going to go through on your own, because we've already covered what is this definitions on energy, right, in previous levels, right? We did so in, I think, in N1, definitely in N2, definitely in N3, right? So that's, I'm going to skip in N4. Are we clear? Hello?
Yeah.
Am I speaking to myself here?
No, we're here, sir. We're here listening.
Weren't you the one who was saying something or wanted to ask something?
Yes, I was the one, but I got too busy, so I disconnected. I don't know. Network on my side is bad.
All
No,
right.
I was asking in terms of trying to remind yourself of certain formulas, because there are a lot of formulas that we keep in the head. Sometimes mixed up on the head, then you might put the wrong formula. You understand? But there are those formulas that when you look, you feel like it can remind you of a certain formula. Then you can be able to remember, not to put yourself under stress and put a wrong formula. Is there a technique that you can use to read that formula sheet?
So if you have the formula at the back of your mind, but you're not quite sure, and you have to go to the formula sheet for that, that's different. Because when you go to the formula sheets, you know exactly what you are looking for, right? So when you get to the formula sheet, you will see exactly what it is that you're looking for, right? So what I was talking about was just having to go to the formula sheet, trying your luck to see if any formula is going to make sense, right? When that is the case, every formula is going to make sense. But if you know if you have the formula at the back of your mind, but you don't quite remember how it goes, then you have to go to the formula sheets. That one is fine, because you know exactly essentially which formula you are looking for, right? But the best way of memorizing formulas is by doing as many problems as possible, right? If you do that, the formulas are going to stick, right? If you've watched me ever since we started, right, I've never went to the formula sheets, right?
Yes.
Right.
Yes.
Yes, sir.
That's not because I'm a lecturer. That's not it. Right. It's
It's
because
because you're a lecturer. It's
no,
part of it.
that's not it. That's not it.
You set the test, so it's part of it.
No, not really. Because My experience with lecturing is 2 years, like literally. So when I started, I was like this. Ever since I started lecturing, I've always been like this, right? But I'm like this because I'm someone who doesn't leave any stone unturned, right? When I look at books, I make sure, my guy. So that is exactly what I'm proposing to you as well, that you leave no stone unturned. Do as many problems as possible.
Noted.
Right. Now let's look at the work energy theorem, right? Now the work energy theorem is based essentially on energy, right? We have, what is this? W net being equal to, what is this? Being equal to the change in EK, right? So this is essentially the work energy theorem, right? W net is equal to the change in kinetic energy, right? Right, W net is equal to the change in kinetic energy. Now this is going to be helpful for you to you in certain exercises, right, where you are able to use this relationship, right? For dynamics, if you have an object and it's moving, right, as soon as it moves, it means there's going to be some change in kinetic energy, right? And that is where essentially this work energy theorem comes from, right? Now W net, if you have a force, right, if you have an object, that object is on a, let's say that object is on a horizontal plane. Right, let's say this object is on a horizontal plane, right? There's your object. Right, you have an object, it's on a horizontal plane. This object has some mass in kilograms, right? And then we get a force being applied here. So you have a force being applied. Applied force, we are going to denote as F sub T. F sub T for total force applied, right? So this stands for the force being applied, the total force being applied, right? Now, if the force being applied is such that it is enough to overcome static friction and this object starts moving in the same direction as the force being applied, it means this will be accelerating in the same direction as the force being applied, right? Now, once this starts moving, it means you will now have another force, right? There's this force that always opposes motion, right? When the object, or before the object starts moving, that force is static friction. When the object is then in motion, that force is, what is this? Kinetic friction, right? We'll just call it friction, right? So friction always opposes motion. So if this is going in that direction, it means you have friction going in the opposite direction, right? And then of course, now this is on a horizontal plane, so the work being done is on the X plane only, right? There is no work done on the Y plane, right? Or on the, let us just say on the vertical plane or Y plane, right? But there are forces on the Y plane. Those forces are the normal force, right? You have the normal force, I'll call R, and then you have the weight of the objects. So the weight of the objects, which is mg, right? So essentially, the normal force essentially cancels the weight and vice versa. Hence, there is no work done in the vertical plane, right? Right. Now, we look at the forces that this object is being subjected to on the plane where the work is being done, right? Now, what am I getting to with this, right? I wanted to mention that if there is a force that an object is being subjected to, and that force is in the plane where the work is being done, there is going to be a corresponding work done due to that force, right? So meaning you have we've established that the work is being done on the horizontal plane, right? Now, on the horizontal plane, which forces do we have? We have Ft, which is the force being applied, and then we have the frictional force. So because we have these two forces, right, it then means there is also some work done that corresponds or that is due to these forces, right? So the first thing you would do here is first establish the vector sum of forces acting on this object, right? In the what is this? In the plane where the work is being done. Now, how do we do that? We look at the direction of forces relative to the direction of acceleration, right? And then we say forces going in the same direction as acceleration, right? Like in this case, the only force going in the same direction as acceleration is Ft. That means Ft is greater than any and all forces going against acceleration. Forces going against acceleration in this case is F mu. So this is F mu, right? Now what does this tell us? This tells us that as far as the vector sum of forces, right, Ft is positive and F mu is negative. Are we clear?
Yes, sir.
That is how you determine what is this? The vector sum of forces from your free body diagram. That is why a free body diagram is very important, right? Whether the object is on a horizontal plane or inclined plane, always draw a free body diagram so that you know which forces the object is being subjected to, and then you look at the direction of those forces relative to acceleration so you can determine the vector sum of forces, right? With the vector sum of forces, the forces going in the same direction as acceleration you take as being positive, and forces going against acceleration you take as being negative. This gives you the vector sum of forces. So essentially, in this case, the vector sum of forces is equal to Ft minus F mu. Make sense?
Yes, sir.
Right. Now, back to my point, right? So essentially, we have these three forces that this object is being subjected to in the plane where the work is being done, right? If you have such forces, right, that this object is being subjected to, it means there's also going to be some work done that corresponds to this force or some work done that is due to this force, right? So if you have F net, you are going to have W net. If you have Ft, you are going to have Wt. If you have F mu, then you are going to have W mu, right? So the vector sum of forces doesn't just tell us the vector sum of forces or the direction of the forces. It also gives us a clue as to the work done that we can expect from the problem we're looking at. Right, so if you have F net, it means you have W net, and that W net will be equal to Wt minus W mu. Right, so this is the net work done, this is the total work done, and this is the work done to overcome friction. Are we clear here?
Yes, sir.
Okay, it seems I'm talking to one person.
How important is it to state that Ft is greater than the F mu? Is that important when you do the calculations?
Not necessarily, no. This is important.
All right.
This is important. This is just for context. You don't necessarily have to do it, right?
All
this
right.
Because even if you just look at the direction of acceleration and you do this, that's fine.
Okay.
Right. So as far as calculations, you do not necessarily have to do this, right? This I am I'm advising for you to do, because before even doing calculations, right, you will have this here, which is very important, right? So from your free body diagram, you are able to establish your vector sum of forces as well as your vector work done, or let us say your net work done. Right? That is why I'm saying it is important to draw this thing, right? Because from it, then you are able to establish this, right? Before you even look at calculations. Make sense?
Yes, sir.
Right. But this part in particular, right? So this here, right? You don't necessarily have to do it. So this, you don't necessarily have to do that, right? The most important thing here is this one, which you can establish by just looking at the direction of the forces relative to the direction of acceleration. Nah?
Yes, sir.
Right. Now, like I said, if you have some force, right, you are also going to have some work done due to that force, right? So if F net is equal to this, then it means W net will be equal to that as well, right? Now we know that work done is equal to force times distance or force times displacement, right? Now this means that if you have F net, your W net will be equal to what? So bearing in mind that work done, the formula for work done is force times displacement, right? So for W net, the force will be F net. So that is what I mean by if you have a force, then you have a corresponding work done due to it, right? So work net will be equal to F net times S, right? WT will be equal to, the force for this one will obviously be FT times S. And then this one, work done to overcome friction, right? The force would be the frictional force times the displacement. Are we clear?
Yes, sir.
All right. Now,
Just a quick question, sir.
yes.
Yes, from that resulting F net, which is equal to the total force applied minusing the frictional force.
Yes.
Looking at an inclined object, that the force has been applied from the bottom upwards, and then all of a sudden the frictional force is greater than the force applied. Is then meaning that you don't have work done at that instance, or is there work done but in the opposite direction, which will lead us to have a negative answer in terms of calculations?
So if there's a force being applied such that you intend for the force being applied to move the object up the incline, if that force is less than the frictional force, then the objects will not move. Right? For the object to move, the force being applied must be such that it overcomes friction. When it starts moving, that implies that the force being applied is much greater, right? Is greater than the force, than the frictional force. Right? So you will never get a case, it's impossible to get a case where the object is going up the incline and yet the force being applied is less than the frictional force. It's impossible.
Let's check it in a case of a car, say, that the handbrake up, and then there's people that are pushing that vehicle up the incline, and then just before they push, the person inside the car, the vehicle, drops down the handbrake, and then say push, it going up, and then it goes down.
Well, it still means there is no force applied. That's what it means essentially. If it starts going down, then it means the object or the vehicle is now using its weight component that is parallel to the plane. That weight component that is parallel to the plane, it is way more than the force being applied by the guys who are pushing the car. So even then, you essentially don't have any work done, or you don't have, or what is this, FT being applied, essentially.
Okay, sir.
You see what I'm saying?
Yeah, I get you, sir. So you only get we only got applied force when the object moves to the direction of where it was intended to.
Basically, yes.
Okay, thank you, sir.
Yes. Yes. Right. Only in a case where the car is now braking. Right. When the car is braking, right? So when the car, when you want to decelerate the car, hence brakes are applied, right? Only in that case would this then fall away, right? Because there is no longer a force that is propelling the object forward, right? Instead, the force being applied now is intended on braking the car or on decelerating the car, right? And in that case, the force being applied you then take as the braking force. Are we clear here? But we'll look at cases of braking forces and how you would attempt a problem based on if the object was moving forward and then brakes are applied.
So you're
So
covering,
cutting out there.
you're covering your mic.
You can't hear me.
We couldn't hear you.
You couldn't
Sound
hear
like-
me.
Yeah, it sounded like you were cleaning your mic or something.
Did you miss the parts of the braking force?
I think that's where you went away.
Right. So I was saying the only time where this will fall away if an object is moving in the direction of the force being applied is when the object is moving and then all of a sudden brakes are applied, right? For whatever reason, right? When brakes are applied, we still have an applied force, but that applied force now becomes a braking force, right? The way we denote a braking force is by using this F sub B, right? But because in that instant, there is no longer a force that is propelling the object forward, right? This falls away, right? And the force essentially being applied then becomes the braking force, right? And the braking force, because it is essentially going against momentum, right? It will be going against, what is this? It will be going against motion, right? So even then, FB will not be negative, it will be positive, right? So there's absolutely no scenario where the force being applied, whether it's FT or FB, will either of these forces be negative. That's my point here. Are we clear?
Yes, sir.
Hello?
Yes, sir.
Yes, sir. Yes, sir. Got you.
Right. Right. Now going back to this here, right? So if you have these forces, right, that the object is being subjected to, then you will have some work done due to each of those forces, right? So that means with W net, now that we've established what it is equal to, right? So W net essentially, right? W net is equal to this, and then of course it is equal to that as well. So the formula to calculate W net, right, is this one. The formula to calculate the total work done is this one. The formula to calculate work done to overcome friction is this one, right? So meaning this, right, can be expanded as F net times S is equal to the change in kinetic energy, right? So this you can use, right, depending on if you are able to calculate the kinetic energy. So if you have, remember what kinetic energy is equal to. Kinetic energy, so EK is equal to half mv squared, right? So again, between mass and velocity, right, only one of these quantities can change since we're looking at solids, and that's the velocity. So that means as far as the change in kinetic energy, the change in kinetic energy will be equal to half m into final minus initial, right? So if you have both of these velocities, you have the mass, right, and you have, say, the distance as well, then you can get F net using this formula, right? Or if maybe we're looking for Ft, right, say we're looking for the total force being applied, right, instead of first calculating F net, you can just substitute F net here. So the Ft minus F mu. So meaning here you can simply say this is Ft, right, from the vector sum minus F mu into S is equal to change in kinetic energy, right? And then you solve for Ft, right? Provided, of course, that that is the only unknown. Are we clear here?
Yes, sir.
Right. So that is the work energy theorem. Work net is equal to the change in kinetic energy. Other formulas that are convenient to know here are obviously equations of motion. Right, equations of motion. We just touched on them when we were looking at kinematics. Right, equations of motion. You have V is equal to U plus AT. You have S is equal to, what is this, UT plus half AT squared. You have, what else? S is equal to the average velocity. So V plus U divided by 2 times what? Times T. Right? This is the average velocity. Right? Average velocity, remember, is final plus initial divided by 2. Right? So that's the average velocity times T. And then you have the last one. V squared is equal to U squared plus 2AS. Right? So you are able to use any one of these formulas, any one of these equations of motion for dynamics as well. Right? Depending on which one is convenient for us to use. Right?
Yes, sir. A
Right.
lot of formulas in dynamics.
Yes, there is. Right? There is. So you must be able to sing them just like me, and you'll be fine. All you need to do is sing these formulas, and you should be fine. Right? If you understand dynamics, in fact, any of the modules, right? If you understand them principally, then you should be fine. Right? Don't be too concerned about answers. Most of you are too concerned about getting answers. Be concerned with the approach. Be concerned about understanding the module from its from the perspective of its principle. What's the principle around the module, right? And the approach, of course. And then either way, if you understand the principle, understand how to approach problems, right? You are going to get to the answer anyway. Right? Don't be too concerned about answers. No. Hello.
Yes, sir.
Yes, sir.
Right. There's one more formula. Well, essentially two more. Right. That is the conservation of energy. Right. Conservation of energy. Right. Conservation of energy. Right. This one is very important too for dynamics. Right. I'm not going to get into the definition of the conservation of energy that we covered in N2 and in N3. Right. If you need to recap, just go to your textbooks. Nah. Otherwise, I'm not going to recap conservation of energy. I am going to express the conservation of energy mathematically, though, right? Because it might happen that you've never really looked at the conservation of energy the way it should be looked at, right? All you know about the conservation of energy probably is that EP plus EK is equal to, you see what I'm saying? And that is not really the case, right? Now, as far as conservation of energy, right, or how we express the conservation of energy mathematically, right, it depends on what exactly you are looking at, right? So when the object, when there's a force being applied and the object is moving in the same direction as the force being applied, right, the conservation of energy, right, or the mathematical expression of the conservation of energy becomes WT plus A. So plus the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy plus the work done to overcome friction. Right. So this here is how we express the conservation of energy mathematically, right? If the object is going in the same direction as the force being applied, right? So this we've already established what it is, right? And then potential and kinetic energy, I would think that you also are familiar with, right? So when an object is in motion, right? When an object is in motion, there's going to be the quantity of energy that you have initially, right? So potential energy and kinetic energy, right? And where the object ends up, right? You are going to have a quantity of potential energy as well as kinetic energy, right? At which point that will be the final potential energy and final kinetic energy, right? And then from the point where the object starts moving to where it ends up, right, there will be some work done to overcome friction as well, right? That is why we have the work done to overcome friction on this side. Are we clear? So this is what I mean. Say you have an object on an incline, right? This object starts at this point. Right? This object starts at this point, right? And say brakes are just released and this starts moving down the incline, right? So this here will be your initial point, and then maybe they say that this ends up, right, at the bottom of the incline, right? So this will be your final. So you will have kinetic energy at this point. You will have potential energy at this point. You're also going to have potential energy as well as kinetic energy at this point, right? Where the object was initially, you're going to get initial kinetic energy, initial potential energy. Where the object ends up, you're going to have final potential energy as well as final kinetic energy, right? And then if you think about it, right, at this point, there is no work done to overcome friction, right? But when the object starts sliding down the incline, right, it is going to overcome friction, right, from this point, right, to where it ends up. That is why we have work done to overcome friction on this side, right? And then as far as the work, the total work done, if there is a force being applied for this to go down the incline, right, you are going to apply this force here, and then this starts moving down the incline. That is why this is on the initial side of things. Are we clear?
Yes, sir.
Yes,
So
sir.
just a question, why are you using a I instead of like a U for the initial?
It doesn't matter. I used I for initial, F for final.
Okay, cool.
You can use U. So how you denote it doesn't really matter to me.
Okay.
But I used I for initial, F for final. Right. So it was just for context. Otherwise, it doesn't really matter what you use to me. No?
Okay, thanks.
Right. So this is when the object is moving in the same direction as acceleration. And then this you get if there is a force being applied. Remember, you can only get total work done if there is a total force being applied. Right? No total force, no total work done. Right? So like in the case we just looked at, right, we just said the brakes were released and the object started moving down the incline. Right? So essentially the object, it moves down the incline using the component of the weight that is parallel to the plane, right? So essentially this will not be there, right? And then potential energy at the top, you do have its kinetic energy, right? When the object was still at rest, you do not have this, right? Final potential energy, that is when the object is at the bottom, so you don't have this, right? The object will have accumulated, right, some velocity, so you're going to have a final kinetic energy, right? And then if they say you have a considerable amount of friction, then it means, right, on the surface, then it means that there's going to be some work done to overcome that friction. Hence, you're going to have this, right? Now, there is this expression that kinetic energy at the bottom is equal to potential energy at the top, right? That is not necessarily true, right? That only applies when an object is free falling, right? So when an object is free falling, then we can say the kinetic energy at the bottom is equal to the potential energy at the top, right? But if there is a contact force being, so we have two contact forces, right? Normal force as well as the frictional force. So if you have a frictional force, right? If you have a frictional force, then we cannot simply say that the kinetic energy at the bottom is equal to the potential energy at the top. Why? Because there's now friction to consider. The object is no longer free falling, right? So it's only when an object is free falling, or if the object is on a smooth surface where the friction is not of a considerable amount, hence we neglect friction. Then in that case, that is the only case where the potential energy at the top will be equal to the kinetic energy at the bottom. Are we clear?
Sorry, sir.
Yes.
In terms of the frictional force that we neglect, mathematically, how do we have a specific number, like
no, we do not have a
an
specific
amount
number.
up to this?
No, we do not have a specific number. What will tend to happen if the friction, if the surface is a smooth one, then they'll just not give you friction. So if you haven't been given friction, right? In fact, sometimes they'll even go as far as even saying that the plane is a smooth one. So if the plane is smooth, then that suggests that friction is essentially tending to zero.
Okay, sir. Thank you.
Right. Right. Any more questions? No questions. Wonderful. So this is the mathematical expression of the conservation of energy, right? When the object is essentially, let's say, accelerating. Let me put it like that. When the object is accelerating, this is what we use, right? Or maybe let me write here. When object is accelerating. Yeah, I think this one is better. Right, when the object is accelerating, and then we have another one, or we express the conservation of energy mathematically differently when the object is decelerating. Right, when the object decelerates, right, what we'll have, because remember, like I explained earlier, that you're still going to have, when the object is decelerating or is braking, right, you're still going to have a force applied, but that force applied will now be a braking force, right? Okay. Right. Now, let's say this here is right. This was headed in that direction, right? But now, right, brakes are being applied. When the brakes are being applied, right, this is what we have. Right, the braking force has to go against momentum, right? So the momentum will be in that direction, and when brakes are being applied, right, the braking force, so that the car is eventually stops, right, the braking force has to go against the momentum, right? Hence, the braking force will be in that direction, right? Also, what will change is the direction of acceleration, right? When the object is decelerating, right? So remember, acceleration is a vector quantity, right? So we say it is pointing in that direction because it was accelerating, right? Now that it's decelerating, right? It's still on this plane and it is decelerating. That it means we need to change the direction of acceleration such that it points in a negative direction, right? So meaning the acceleration will also change direction and be in that direction, right? So there are no more forces, right, in the direction of motion, essentially, right? Now you do the same thing even here, right, for your vector sum of forces, right? You look at the forces that are in the same direction as acceleration, take those as being positive. That means the vector sum of forces, right, F net will be equal to, now if you look at the forces that this object is being subjected to, you have the braking force and the frictional force, both of which are going in the same direction as acceleration, meaning that they are both positive. So Fb plus F mu, right? Are we clear? So when braking is taking place, this then becomes your free body diagram, right? And then when it is, this then becomes your free body diagram, right? And then if this is your free body diagram, then it means this is your vector sum of forces. And you determine your vector sum of forces, right, by doing what? By looking at the direction of the forces relative to the direction of acceleration, right? Now, another
Yes,
thing
sir.
to note is that if you look at the braking force, right, the braking force you will only get once the object is already in motion, right? So meaning what? As far as your conservation of energy, you are only going to get a braking force, hence the work done due to the braking force on the what? On the final side of things, right? So remember, you have the initial and you have the final side of things, right? So meaning this, seeing that the object is already in motion, you are going to get on the side of the final side of things, right? Any questions here before I remove this thing? Hello?
I said yes, yes, yeah. It is the way you say it. But I have a question, say on according to Newton's law of motion, third law, it says most the forces to the right hand side is equal to the forces to the left hand side.
Yes.
And then in this case, we actually come to a state where we ignore that because it only happened before the braking force was taking place.
We did not ignore it. Remember, forces forces on the right being equal to forces on the left. So Newton's third law of motion, it applies only when you have only when the object is static, right? Only when you have equilibrium. If the object is in static or dynamic equilibrium, then we can say that. But the object here is not in dynamic equilibrium or static equilibrium, so it doesn't really apply Newton's third law of motion.
Okay.
Remember,
okay,
in Newton's third law of motion, absolutely nothing is happening. It's like you pushing against the wall. Absolutely nothing happens, right?
Yes.
That is static equilibrium,
yes.
right?
So
Static equilibrium means that F net is equal to 0. When F net is equal to 0, then you essentially have Newton's third law of motion. That is why even under when an object is moving at constant velocity, right? Constant velocity means that there's no acceleration. No acceleration means that F net is equal to 0. When F net is equal to 0, then you have equilibrium, right? Hence me saying static as well as dynamic equilibrium, right? Which in this case you have neither. Am I making sense here?
Yes, I got it. Because I can see now because forces acting to the right and forces acting to the right, they are in equilibrium, which is there's no acceleration. But in this scenario now, we do got acceleration, but
Yes.
then it's not that in the same direction with the frictional force.
Yes. 100%. Right? Any more questions? Right, no questions. Right. So as far as how we express what is this? How we express the conservation of energy mathematically when the object is braking or when it is decelerating, right? It is going to be initial potential energy plus initial kinetic energy is equal to, right? Then when you have, like I said, if you have a force, right, that an object is being subjected to in the plane where the work is being done, then you are going to have some work done due to it, right? So here you would then going to have the work done due to braking plus the final potential energy plus the final kinetic energy plus the work done to overcome friction. Right? These formulas are going to come in very handy. Are we clear here?
100, sir.
Right. Okay. Right. Now let us look at an example. Right. Let us look at an example. Okay. Let us look at an example. Let us look at an example. Right. So let us look at this simple one first. Right. So we're going to look at one where the object is accelerating, and then we are going to look at one where the object is decelerating. Right? Dynamics is all about knowing your principles, knowing your theorems. If you know your principles, right, Newton's laws of motion, you know the different theorems we use. So the work energy theorem, the impulse momentum theorem, which is what we use to essentially get Newton's second law of motion. I am telling you, how we express the conservation of energy mathematically when the object is accelerating or decelerating. I am telling you right now, this will be a walk in the park for you. All right, this will be a walk in the park. Dynamics is like 14% in the exam, so don't mind this 8%. In the new syllabus, dynamics weighs definitely more than this. It's like 14%, so 14 marks. Right now, that 14 marks can be either a Christmas present to you, or it can be hell. Either way, the decision will be yours. Nah? Because dynamics is very easy. All right. Now let's look at this example. Right. A vehicle with a mass of 980 kilograms accelerates uniformly up a slope of 1:45 from 6 meters per second to 21 meters per second within 35 seconds. The resistance to motion is 0.459 newtons per kg. Right. Now, if you look at how the resistance force, so the frictional force has been expressed here, it is expressed in terms of newtons per kg, right? So this suggests that to get the frictional force, we need to get rid of this kg. The way we're going to get rid of this kg is by multiplying this by what? By that mass. Is that clear to everyone?
Yes, sir.
Yes, sir.
Right. So also we have an inclined plane here. Right. We have an inclined plane. So this is on an incline. I don't have one. Okay, there. Let's use this one. Yeah, this one work. Let's use this one. Right. Inclined plane. Now, with inclined planes, right? With inclined planes, I want you to have a look at this. Right. The way we essentially look at the Cartesian plane on an inclined plane, right, is from this perspective. Right. An inclined plane is essentially one that was horizontal, or the way we look at it, right, is that it was horizontal and then now it is inclined. Right? So what tends to happen as far as the Cartesian plane is that the Cartesian plane will also be at an incline, right? So when the plane is horizontal, that is your Cartesian plane. So the orange Cartesian plane, do we see it here?
Yes, sir.
Right. So that's a Cartesian plane when the plane that is a Cartesian plane. What is this? I don't think I'm calling this right. What is it called?
The Cartesian plane is.
I'm right. So the Cartesian plane is essentially like this when the plane we are looking at is horizontal, right? But now when the plane is inclined, right, the Cartesian plane will also be at an incline. So that is what happens essentially, right? So essentially, we know that okay, let me do this. So we know that this here is the x-axis, that's the y-axis, right? So on an inclined plane, right, the x-axis are gonna be like that essentially. There. Okay, there, right? So these will be your x-axis and this will be your y-axis. Right, so my point here is that the Cartesian plane will also be at an incline. Are we clear?
Yes, sir.
Yes, sir.
Yes.
Right. Oh yes, this is inclined. So that's your inclined plane, right? And then you have your angle of incline at that point. Now they said that this accelerates uniformly up a slope of 1:45, right? So if they've given you a slope, all you do is you say tan theta, right? This theta, the angle of incline, is equal to the slope. So tan theta is equal to the slope. So this is equal to the slope, right? And the slope or the gradient thereof is 1:45, right? So you simply say tan theta is equal to 1:45. 1:45 is the same as 1/45. So that's 1/45, right? And then to calculate theta, you obviously calculate the arctan of 1/45, right? And what is theta equal to?
One comma 273.
All right. So 1,273 degrees, right? So that's the angle of incline essentially, right? So that is how you calculate your angle of incline. So sometimes the angle of incline, they don't give you as an angle, you are given the slope. Sometimes you're given the percentage, right? It can be expressed in a number of ways, right? But for the most part, you are always able to get it using this here, right? On the exercise or on the handouts I'm going to give you, you are going to see a couple of ways that it can be expressed in. So if you struggle with that, just give me a shout in the WhatsApp group, and I will help you with that. Right, but first try it on your own, and then only if you struggle, then you can let me know, and I'll help you. Yeah.
Yes, sir.
Right. So we have our angle. Right. Also, I would advise that you do not. Now the what is this? Sine theta can sometimes be equal to or can be approximately equal to tan theta, right? Now this relationship I don't want you guys to use, right? Do not use this relationship. This relationship only applies when this angle is small enough, right? When this angle is small enough, then you have this relationship, right? Hence, instead of using tan theta, you are able to use sine theta, right? Remember here, we have uh, we have this here, right? We have the weight is always acting perpendicular to the ground, So you have the weight, right? Now, if you look at the weight, right, relative to the Cartesian plane, right, it then becomes, okay, I want to be as accurate as possible here. So let me put this there. Okay. Okay. All right. Right. Now the weight of the object, right, whether we are looking at whether the object is on a horizontal plane or an inclined plane, right? The weight of that object will always act perpendicular to the ground. So this here is the ground, right? This here is the ground, and this being the ground means that the weight of this object, is going to act perpendicular, right, to the ground, right? Now, what that means is, right, if you look at the weight, right, relative to the Cartesian plane, it then becomes an oblique force. Do you see that? Because it is at an angle. It doesn't align with either the x or y axis, right? Hello?
Yeah.
You guys remember oblique forces? What do we do with oblique forces? So oblique forces, we resolve them into their components. Yes.
Yeah.
Right. In order for us to be able to apply conditions of equilibrium, right, the forces that we use must be such that they are parallel to the axis. So either the y or x axis. That is why we need to resolve this into its components. So you're going to have that component, right, a component that is parallel to the plane, and one that is perpendicular to the plane. So this one is perpendicular to the plane. This one is perpendicular to the plane. And then this one is parallel to the plane, right? The one perpendicular to the plane we'll call FG perpendicular, and that one is equal to the weight cos theta. And then this one we will call FG parallel, right? So the components of the weight parallel to the plane. This one is weight sine theta, right? So this is what I'm coming to, right? So this here, right? Instead of if the angle is small enough, right? So theoretically, if the angle is small enough, then this is approximately equal to that. So instead of having to calculate theta using this way, right, you can simply just equate the slope to sine theta, right? So because tan theta is equal to the slope, for such a case, it means also sine theta is equal to the slope. So you can replace sine theta, right, with this 1/5. But what I'm saying to you is do not use that approach, right? Because you will never know if the angle is small enough such that sine theta is approximately equal to sine theta. Sine theta is approximately equal to tan theta. So always take this approach. This approach is much safer. Are we clear?
Yes, sir.
Yes, sir.
Right. Again, never take this approach. This one, do not use it. Right. Do not use this approach. Right. This approach is for us. Yeah.
Sorry, sir.
Yes, sir.
I hear you that you trying to emphasize that we mustn't use that approach of sine theta is equal to tan theta.
Yes.
Normally, that for you guys that are using it, do you normally use it for the case of getting the size of that angle theta?
No. It's a matter of convenience. If I've established that the angle is small enough that sine theta is approximately equal to tan theta, right? It then means if tan theta is equal to the slope being this, it means in that case this is also equal to sine theta, right? So meaning for FG parallel, since it is equal to W sine theta. Once I've established that the angle is small enough, instead of having to calculate the angle, I can just replace sine theta with the slope 1/45. So do you see what I mean?
Okay, I got you, sir.
right? It's a matter of convenience. But like I said, this only applies if the angle is small enough, and you won't be able to tell if the angle is small enough, right? So because of that, it is convenient that you stick to only this here. Only use this approach. Always calculate the angle and use the angle. Nah?
All right, sir.
Right. Where was I? Right. So this is our free body diagram. Right. Now we've already established two of the forces that this object is being subjected to. You have the components of the weight. Right. This is going up the incline. If it is going up the incline, it then means you have a force being applied. Right. You have a force being applied, right, in that direction. So you have Ft. This is accelerating up the incline. So acceleration is in the same direction as Ft, right? And then we have the resistance to motion. That resistance to motion, right, we know it is going to be in this direction, right? Always opposing motion. Let's make this green. Right, so you have F mu in that direction, right? And these are all the forces that this object is being subjected to, right? I just lied. You also have the normal force. Right, you also have the normal force. So these are all the forces that this object is being subjected to, right? So once you're done drawing your free body diagram, from your free body diagram, you will be able to establish the vector sum of forces, right? By looking at the forces going in the same direction as acceleration, right? Forces going in the same direction as acceleration is Ft here. That means as far as the vector sum forces, right? Ft is positive, so this will be positive, and then forces going against acceleration, right, will both be negative. So this is minus Fg parallel minus F mu, right? So that becomes your vector sum of forces, right? So once you've established that, then you can look at calculations. Calculations will be much easier now that you've established your vector sum of forces. So the question 5.1 calculates the acceleration of the vehicle. Right? If you look at the statements, we've been given the initial and final velocity, and we've been given the time as well. Right? So this will be a matter of just using an equation of motion. Right? So 5.1, you simply use an equation of motion. Acceleration is equal to the change in velocity, which is v minus u divided by t. Right? So now all you do is substitute. Final velocity was 21 meters per second. So this is 21 minus the initial, I think it's 5, no, it's 6. So this is 6 meters per second divided by the time, which is 35. Right, 35 seconds. Are you guys still with me?
Yes, sir.
I'm talking to all of you.
Yes, with you, sir.
Right, so what do we get here? What is 21 minus 6 divided by 35?
It's 0,429.
0,429 meters per second every second, right? 5.2, accelerating, so calculate the accelerating force of the vehicle. All right, so accelerating force is the same as F net. Right, so F net and accelerating force or inertial force, that is one and the same thing. All right. So they're essentially wanting us to calculate F net. Right, we've calculated acceleration, right, and we have the mass. So it will be a matter of just applying Newton's second law of motion here. So F net is equal to, as we know, ma. We have the mass. The mass is 980. Acceleration, we've just calculated 0,429. Right? And what do we get here? Is it 5? 980? Yes, it is. So what do we get here? What is 980 times the acceleration?
420. Comma 42.
0.42, that is newtons, right? Easy peasy. 5.3, calculate the total force, right? So they want us to calculate Ft. See, now that you've already established that this is the vector sum of forces, right? So you're going to use this and then make Ft the subject of the formula. This you've already calculated. This you can get, you know, it's equal to W sine theta. Theta you've already calculated, right? You are going to calculate the weight, and then F mu, right? F mu we know is equal to that. So let us first calculate the weight as well as F mu, and then simply use this relationship and then solve for Ft. All right, so let's first calculate the weight. Right, the weight is equal to, the mass is 980. 980 times G. Now for science, G is 9.8, unlike in Meccano. Right, so for engineering science, right, G is 9.8, or we take G as 9.8. For Meccano techniques, we take it as 9.81. So what is 90 times 9.8?
960.4.
960.4.
Yes.
So this is newtons, right? Right, and then 0.459. So F mu is equal to 0.459. This is in newtons per kg, right? To get rid of the kg, you multiply this by the mass. So this will be times the mass, which is 980. And what do you get here?
.449, 82.
449.82. Right. This is newtons. Right. So we have the weight and we have mu. I mean F mu. So we can get now Ft. Right. Using the vector sum of forces. Right. We know the vector sum of forces are equal to this. Right. Solving for Ft here, it would then mean Ft is equal to, so you transpose both of these terms. So they're negative this side. When you transpose them, they will become positive. So this is F net plus Fg. Okay, maybe let's say instead of just Fg, let's use W sine theta plus F mu. Right. So now we substitute. Right. F net is equal to 420. So this is 420.42 plus the weight is 960.4. So 960.4 sine theta is 1,273, right? Plus F mu. F mu is 449.82. And what do you get here?
Sir,
Yes?
regarding the weight, sir, I don't know where the comma is. Where does the comma come from?
Yeah, there's no comma there. It's 9604.
Oh,
9,000. Okay. Yeah.
Okay. So it's like this. No, it's like
Correct.
this.
Yes, sir.
Correct.
All
Yes.
right. Okay. So there. Right. Now what do we get here?
Uh, 1,083.
1,080. So 1,083. No commas.
Comma 605.
605. Are we getting the same thing here?
Yes, sir. Correct.
Yes, sir.
Right. So that becomes our Ft, right? And that's the approach you would take. So essentially, this is a matter of understanding your approach. Right? Once you've drawn the free body diagram, problems on dynamics just become easy. Nah, any questions? No questions. Wonderful. So let us move on to the next example.
Sorry, sir.
Yes.
Can I quickly see how you calculated EVU?
How I calculated what?
The frictional force.
Oh, there. So remember this was expressed as 0.459 newtons per kg, right? So you want your frictional force to be expressed only in terms of newtons. So it means you need to get rid of this. How are you going to get rid of this? By multiplying that by the mass. And the mass is 980. Right? Remember the mass is in kgs. Right? So this will get rid of that, and you'll only be left with newtons. Make sense?
It makes sense, sir.
Wonderful. Any more questions? All right. Now let us look at this one. All right. You have a car with a mass of 1,200 kgs is traveling on a horizontal plane at 120 kilometers per hour in a 60 kilometer per hour zone. The driver notices a speed trap 30 meters away and applies the brakes so that the car moves at 60 kilometers per hour through the speed trap. The resistance to motion on the plane is 0.183 newtons per kg. Right, so again, they've given us they've expressed the frictional force in terms of newtons per kg. Right, and as we've established, to express this in newtons, it means we need to get rid of that kg by multiplying this by the mass. Right, but first thing is first, let us draw our free body diagram. Let us draw our free body diagram. Okay. All right. All right. So this is our free body diagram. All right. We can remove this. Yes. Right. So this is our object. Right. This is our object, and this here is our horizontal plane. Right. They say a car with the mass of this traveling on a. So this is essentially decelerating because remember, if you look here, this is traveling on a horizontal plane at this speed. Right. In this zone, the driver notices a speed trap that is 30 meters away, right, at the point where he notices the speed trap and applies the brakes so that the car moves at 60 kilometers per hour, right? So we are decelerating here, right? If you are decelerating, it means this object is already in motion. So the momentum is such that it is in that direction, for instance, right? So to kill this momentum, we then apply a braking force. That braking force must be such that it is opposite the momentum, right? So essentially what you have, the motion is in that direction. So because the motion is in this direction, it means the frictional force will be in this direction. So the frictional force we know is in this direction. Right, so you have a frictional force there. This is F mu, right? And then we also have the braking force. Right, you have the braking force, right, in that direction. And because this is decelerating, it means acceleration is in that direction, right? Now, of course, we will always have the normal force here and the weight there. So that's the weight, all right? So this is our free body diagram. Now, what do we get from a free body diagram? We get the vector sum of forces. Now, what is going to be the vector sum of forces here? We look at the forces that the object is being subjected to in the plane where the work is being done relative to the direction of acceleration, right? So as far as the forces, we have the braking force as well as the frictional force both going in the same direction as acceleration. So that means both are positive. So plus F mu. Are we in agreement here?
Yes, sir.
Yes, sir.
Right. So this is essentially a free body diagram, right? And from this, we then establish the vector sum of forces. Now we can look at questions, right? Before we look at questions, let's establish exactly what it is that we've been given. So we've also been given the mass. The mass is 1,200 kgs. What else have we been given? You've been given the initial velocity. It's 120 kilometers per hour, right? We work with meters per second here. So as far as what we've been given, right, let us calculate the initial velocity, right? So how you convert from kilometers per hour to meters per second is by simply dividing the magnitude by 3,6. So you have 120, you divide this by 3,6. And what do you get here?
33,333.
So 33,3 recurring, so 3 decimal places, meters per second, right? Now the final velocity, right? The final velocity, right, is going to be this 60 kilometers per hour, right? So you do the same thing, 60 divided by 3,6. So what do we get here? What is 60 divided by 3,6?
16,667.
So 16,667 meters per second. Right, so that's the initial and final velocity. What else have we been given? So the fact that the driver notices this speed trap 30 meters away, right, that suggests that this here is our distance. So we have S. S is 30 meters, right? And then we're also given the frictional force. So the frictional force will be equal to that 0,183, right? And then of course you have to multiply this by the mass, so that the frictional force is expressed in terms of newtons. So we multiply this by the 1,200, and what do we get here?
219,6.
219,6 newtons. Right, so that is the magnitude of the frictional force in newtons. So essentially that is everything that we've been given, right? Yes. Now let's look at questions. Determine each of the following. Deceleration of the car, right? Based on what we've been given, we have enough quantities, right, that we can use to calculate the deceleration using equations of motion, right? You have both the velocities and you have S. So the most convenient equation of motion to use here is this one. So 4.1.1 v squared is equal to u squared plus 2 as, right? And then making acceleration the subject of the formula here, this will be equal to v squared minus u squared divided by 2s. Now all you do is simply substitute. The final velocity is 16. So 16,667 all squared minus initial velocity, which is the 33,3 recurring squared, all of this divided by 2s. So 2s is 30. Right? And what do we get here?
Minus 13,888.
Minus 13, 888 meters per second squared. All right, so that means that essentially means the deceleration is equal to 13,888 meters per second every second. All right, are we getting the same thing here? Let's see.
Yes, sir.
Right.
Yes, we do.
Yes. Right. Now let us look at any questions. Probably not. That was pretty straightforward. Right. 4.1.2. Now they want us to calculate the braking force, right, on the car. All right. They want us to calculate the braking force on the car. All right. So that is the FB. All right. They want us to calculate FB. Right. Now there is a couple of options that you have here. We can use the vector sum of forces, but you obviously would first have to calculate this. Right. And seeing that we have, okay, because I want to show you guys why it is important to know the different approaches you can take, right? So that you have a plethora of options in the exam, right? Whichever one comes to mind, you use that one, right? And also, sometimes in a question, you will have information that is convenient to use a certain approach, right? Not just any approach, right? So that is why it is important to know any and all approaches that you can use, right, to solve a problem, right? Now here, like I said, we can simply just use the vector sum of forces. We have this, and essentially we have that because we have the acceleration now, right? So we can get this here, right? Now we know F net, right? We know F net, the vector sum of forces is equal to this. Right? And then F net we know is equal to MA is equal to, or maybe let us say, from this, you then solve for or make FB the subject of the formula. So FB is equal to, so it means you need to transpose this to that side. So essentially you'll have F net minus F mu, right? F net we know is equal to MA, so this minus F mu, right? Then you substitute here. The mass is 1,200. The acceleration is 13,888 minus F mu, which is 219. So 219,6, right? Now notice here that we what is this? We substituted our acceleration as being positive, right? The reason for that is because we've already considered acceleration when we came up with the vector sum of forces, right? When we came up, or when we established the vector sum of forces, it was in relation to what? To the direction of acceleration, right? So when coming up with this, we've already considered acceleration. So which means that if you substitute your acceleration as being negative, it means you are considering acceleration again. Do you get what I'm saying here? It means you will have considered acceleration twice, right, under the same vector sum of forces. Right. That is why here you substitute this as being positive, because you've already established, or you've already considered that it is going in a negative direction. Hence, your vector sum of forces came up to be exactly this. Are we clear here?
Yes, sir.
Yes, sir.
Right. So this is particular only to the vector sum of forces. Right. We substitute this as being positive because essentially we've already considered that direction of acceleration. Remember, the negative, right? This here, right? This pertains to the direction of acceleration, and we have already establish that this is going in that direction, right? And then in establishing the vector sum of forces, right, we look at the direction of the forces in relation to what? To the direction of acceleration. So we've already considered that direction of acceleration, right? So it would essentially be like a double negative, if you will. Are we clear here?
Yes, sir.
Yes,
Right.
sir.
So what do we get here? So what do we get here?
It's 16446. So it's 16,446.
446. No commas.
Newtons.
No,
No,
no
no.
comma.
Right. Newtons. Right. So that becomes your braking force. Right. Now, an alternative method. Alternative method. Right. Would be seeing that we have both the initial and final velocity. Right. Will be the work energy theorem. Right. From the work energy theorem, we know that W net is equal to the change in kinetic energy. What is W net equal to? W net is equal to F net times S, which is then going to be equal to half M V squared minus U squared, right? Now, what is F net equal to? F net is equal to, we know F net is equal to this here, right? But now, remember here, right? In this, in the work energy theorem, we haven't necessarily considered, what is this? We haven't necessarily considered acceleration, right? So when you substitute your F net, it must be such that it is negative, right? So because of that, taking that into account, we then would have to say this is negative into what F net is equal to. F net is equal to that. So this would be FB plus F mu times S is equal to this. Right. And then when you look at what you have now, you're looking for FB, you have this, you have S, you have the mass, you have both of these quantities. So you can solve for FB. All right, so you simply substitute now FB plus F mu, which is 219,6 times S. S is, what is S? I think 30, yes, is equal to half into the mass, which is, the mass is 1,200. So that's 1,200 times V. The final velocity was 16,667 squared minus the initial, which was 33,3 recurring squared. Right. Now we get rid of the parentheses. Right, to say this into that. So here you'll have negative 30 FB. So minus, what is 30 times 219,6?
6,588.
6,588
588.
is equal to, and what do we get this side? What do we get here? What is this equal to? Hello, people.
I think I get like minus 499,980.
Minus
I should get that.
Minus
4,
499,000.
4,000?
499,980.
499,000.
Yes. Yes.
400. Okay, my mind is kind of stiff here.
Four
Yes.
499
499
80.
80.
Yeah, boy.
No commas.
No commas.
Right. So then all you do here is take this to that side. So this will be negative 30 FB is equal to, so obviously this side remains the same, right? And then this is negative this side. So when you transpose it, it will become
Positive.
positive, right? And then we are looking for FB. So you divide both sides by this negative 30. Right, so that cancels. And what is the value of FB? We should get the same thing as we got earlier.
Yes, sir. We get the same answer and then comma 4.
Same answer is, so 16,446, comma 4 newtons, right? Which is approximately the same, right? So you have all these approaches are available to you, right? You use whichever one is convenient. Nah? So my point here is that
Yes, sir.
all the approaches, right, are going to work. You are going to get approximately the same thing. Nah?
Yes, sir.
Right. That was 4.1.2. Right. So let us leave 4.1.3 and 4.1.4 for you guys to do as homework. No?
Okay, sir.
Yes, sir.
All right. So 4.1.3 and 4.1.2, you guys are going to do for homework. I'll also send a document that has a lot of tutorials that you guys can go through. Right?
Yes, sir.
Essentially, the approach is the same. If you know your Newton's laws of motion, you know your equations of motion, you know all the different theorems. So work energy theorem, impulse momentum theorem. You know how to express the conservation of energy mathematically when the object is accelerating as well as when it is decelerating. That is dynamics, guys. Absolutely nothing else to it. Nah?
Yes, sir.
Any questions?
No questions, sir.
All right, wonderful. Wonderful. Right, so
Yes,
let
sir.
us end
Sorry,
this.
sir.
Yeah.
Sorry,
Yeah.
sir.
Yes.
Would you please send the whole document that we gone through, not only the ones that we need to do as homework?
Yeah. So you mean what we did today?
Actually, the activities that we have done, like the questions that we just covered now, just send those questions as well with those ones that we have to do as homework.
Yeah, we'll do so. So I'll send
Yes,
the PDF of what we covered today. All right. So the questions as well as the solutions, and then that other documents I mentioned as well. No.
Yes, sir.
Yes, sir.
All right. If there are no more questions, have yourselves a wonderful evening, guys.
Same to you. Thanks for the lesson.
All right. Cheers.
Thank you very much, sir.
Sharp.
Thank you, sir.
Bye.